All right, so we went through this first one yesterday a bit. Are we good on this one? Now what you're doing there is you're just finding the stress on AB. So you want to use the angle from the vertical to that plane, and that's 25 degrees. Okay. And you just plug that into the formulas, right? So there's the first formula, the normal stress formula. And you just plug in the 2.2 for sigma x, the negative 0.5 for sigma y, and the 1.1 for tau xy, and the angle of 25 degrees. Twice the angle is 50. You want to double the angle so that that's what goes into the formula. And this is formula 25 here, and you get 2.56 positive. Okay. And then when you do the shear, you just use the exact same information. The angle is 25 degrees there. And you go ahead and you run the same equation, or do the shear equation this time, which is equation 26, with the same inputs. Sigma x is 2.2, sigma y is negative 0.5, tau xy is plus 1.1, theta is 25, 2 theta is 50. Plug that in, and you get the shear on the plane. So I was mentioning that yesterday. If there's two different things you can do with this biaxial stuff. One is find the stress on a given plane at a given angle, okay? If that's what you're asked to do, you just plug the stuff in and find it. Don't overcomplicate it, okay? So, all right, so we got to that. We did that yesterday too. Are we good with that?
So for sigma y, we would add 90 degrees.
Yeah, right. If you wanted sigma y, now you don't need it on this one because you're not asked. On this one, you're just finding the stress on that plane.
Oh, okay.
Because the other ones were an element where you had, on the previous problems, we've had like an element where you had two planes. So you would have had something like that. Here, we're just saying, what's the stress right there on that line? Because we got a grain of wood running through there. So it's different, okay? So we don't need sigma y on this one, okay? So if these stresses were to cause that board to fail, to break, what would it look like now? What's it going to do? It's going to pull apart, right? Because it's tension. Good. So there are the stresses acting on it. The shear is negative, so I think of that as being drawn like a negative couple about some point in the middle here. So that both those shears would cause a clockwise spin, which is negative shear. And then the tensile stress, the normal stress, would just pull the board apart. So it'd do something like that. We're good? So just split it apart, pulls apart. It also might move down a little bit. The right side might move down, the left side might move up because of that shear. So we good with that? Okay. All right. Now we've got how about the second one? Are we doing okay on that? And for those of you online, I'll show you that in a minute. Okay.
That's more of the actual piece itself, not just the fault for the second one.
The second one? Yeah. Okay, this one, the question on this was to find the stress at this angle, which was 25 degrees. The next one is different because what we're saying is of course, when you do these things, you have stresses acting in all different directions. So this one is what's the biggest stress in here? Okay, this is ceramic. Things like ceramic and concrete and things like that, they're made out of little grains. They don't lap a whole lot. And so if something doesn't lap a lot, it doesn't have much tensile strength. What gets you tensile strength is when two things overlap, like fibers in wood or something like that. That's one thing, anyway, that's one thing, it's your tensile strength. Okay, so a ceramic probably would not be very strong in tension, so this is weak in tension. So what's the largest tensile stress in the plate?
It's like Mohr, where we find the angle and
Yeah.
check in plane and out of plane.
Yeah, this is different than the previous one. In this one, you have to find the angle first, and you do that with that tangent to theta formula, which is 27. Okay, find the angle. And see, the angle that you find in equation 27 is one of the angles, or actually both of them, where the maximum and minimum normal stresses act. So the first thing to do on this would be to find the angle. Once you've found the angle, then find the stress at that angle. Now you have to do a little bit of analysis on this because one of the angles won't, there's only one largest tensile stress at one particular angle, but you're going to find two angles with that tangent 2 theta formula. So you kind of have to figure out which angle is the one to use after you calculate it, okay? So when you run the numbers, you should come up with about 11.6 degrees for the angle. You don't get to that? Now what's the other angle then? If the first one's 11.6, what's the other angle? Yeah, just add 90, right? So these two angles are 90 degrees apart. Okay. All right, so what we just found is the angles at which these maximum and minimum stresses occur. Look, it's probably something like that, right? Y'all good with that? I thought I got positive when I ran it. I don't know, but what I'm showing right there is positive. No, I got positive 11.6 when I ran it. That's just what comes out of the formula. Is that right? Okay. Yeah, the shear on that, what you plug in is negative 15 because it's a clockwise shear. Okay. All right. So when we run these numbers, if we draw this up, we're going to get an element kind of like that, and there's 11.6 degrees. Now, which plane do you suppose is going to have the biggest tensile stress? And let's not get all analytic here. Just look at the dang thing, and what do you think? If you looked at it, which one of those two planes? And there's only two planes. I mean, there's AB and then BC, okay? So we got AB, and this one's AB also. They're parallel, so they're the same plane. And then we've got BC and BC. So which one do you think of the two would be the one most likely to have the biggest tensile stress?
AC has some pressure on it, so BC has tension, so probably easy.
Yeah, I think so. And why is that? Why, just from a purely common sense, not even touching a calculator perspective, why is BC the one to have the biggest tensile? Yeah, it's the most in line with this one, which also has the biggest applied tensile stress. It makes sense to me that the angled one that's most in line with that would have the biggest tensile stress also, right? You get it's just kind of common sense. Okay, we good? All right. So, all right. So we can go through this and we can run the numbers, and we can take these angles and plug them into equation 25 and find the numbers. Okay. Okay. So when I run the first one, I got negative 13.1. Now, from a mathematical definition, you might call that the minimum stress, but from my engineering perspective, that's what I would call the maximum compressive stress. It's the most negative stress. My engineering thought makes me think that's the biggest compressive stress. If I'm designing for compression for some reason, that's what I'm going to design for, okay? So even though mathematically it's the minimum stress, I might express it a little differently when I describe it, okay? And that's at 11.6 degrees. All right. So we good with that? Okay. And that's just found from plugging those numbers into that equation. I mean, that's really about it. Okay. All right, now once you've got that, how would you find the stress at 90 degrees off of that at 101.6? Let's say you're in a bit of a rush, like you're on a test. You got to knock it out quick. What are you going to do? Yeah, that's shortcut. Yeah, right. That's the thing to do, all right? Now, if you're doing homework, you got a spreadsheet or your programmable calculator, just plug the other angle in, bang. But if you don't, the quick way to do it is with that other formula, okay? So I ran it the full way there, or I just used the shortcut formula. Either way you do it, you come up with the same number, of course, because you're getting the proper answer. It's 63.1. All right. All right. So what we've just done, we found the angles at which the principal stresses act, and then we found also what they are, okay? So why don't you draw a sketch that shows them, these principal stresses, how they're oriented. So what do they look like? See, because keep in mind what we've got to figure out. We've got to figure out how to reinforce this thing so it doesn't break, okay? That's our job here. So we need to figure out how to do that, and I think a sketch is going to help us to figure that out, okay? Y'all get into a sketch okay on that? Good? Something? Maybe not. Something like that for the sketch? No? Other way around? That's why I like doing this, see, because some people are afraid of making mistakes, but you see, when you make mistakes, man, that's when you learn it, right? Hopefully, anyway. And, it makes the point. It's a good way to do it. So that's how we learn. That's the way to look at that. Yeah, well, yeah. See, I was looking at it differently. I was thinking, I don't like doing it on the working, man. Sometimes stuff breaks. I don't like that. But anyway, all All right, so are we good with how I got those? Are there any question on how those sketches were generated? Or that sketch was generated? Okay, now what's the shear on those planes? On those planes that are drawn there, what's the value of the shear? I'll give you a hint. It's not very big. Yeah. And you know, I kind of remember that because where the normal stresses are maximum, the shear's zero. You're not getting that kind of differential to get you the sliding is what's happening. Okay. I find that an easy way to make an easy connection to make. Where the normal stresses are maximum, the shear is zero. There's no shear on those planes. It's just pure compression and tension. Okay, so that's what's going on. Okay. All right. Yeah.
We've got two angles that we're using
right.
to get to these two values, but
Correct.
in the sketch, like, how do we know which
okay.
which angle?
Yeah, sure. How do we know which angle goes with which stress?
Well, I know which angle goes with which stresses of our formulas, but
yeah.
when you made the sketch, you chose one of the two angles, right? It looks like you used 11 points.
Yeah, I did. It was just easier for me to draw. So what I do, I start at the vertical. That's the reference. Right. Counterclockwise because it's positive, and I just took the first angle, 11.6.
Okay, that's what I was wondering. Why? Because you got both the values in there, but only
I do.
one of the angles. Like, could you have done 100?
Oh, sure. Yeah, I could have done it the other way too.
The same thing?
Yes.
Okay.
Yeah. And, you know, I know that, and I did it purposely where I plugged in the angle to get that stress, and then I plugged this angle in to get the other stress. So I know which stress goes to which angle. You know, had I done it the other way, I just sort of been a vertical plane, 101.6. But what would have been going on then was I would have known that at 101.6, I got 63.1 normal to that plane. So I would have ended up with the same sketch at the same orientation.
Oh, okay.
This would have been 63.1, and that would have been...
So if you drew, I see if you drew off that, you drew a line right to the bottom of the box there, that angle off the, what's going on the second.
Yeah. Okay. Okay, that's good. All right, we good with that? Okay. My eraser isn't working. I'm having computer problems here today, but here we go, eraser. So do it that way. Here we go. Oh, jeez. All right, and I didn't draw those quite right, but there we go, and that is 13.1. All right, so how are you going to run the rod? If you don't want that plate to break, how are you going to run the steel rod through it? Yeah, you're going to run it, so you're going to, from the vertical plane, what angle are you going to run the rod at? Yeah, because you want to, see what the rod does is it's going to absorb the tension for you. Okay, so if you're going to put steel rod in there, run it like that. Because then it'll take the pull. Okay. You good? Good to go. So if the strongest tension, which is a pulling stress, is going that way, I want to align the rod right with it because that way the rod will absorb that tension. It'll help do that. I don't want to orient the rod 90 degrees from that because then it'll have these gaps between the rod that'll just crack. It'll just pull right there, okay? All right, good? So that's the significance of what we're doing here. And it's kind of this odd part of the course, but it is something that's important. You know? You got to identify the biggest stress so you can design for it properly, what you need to do. Okay? All right. Any questions on that bit? Okay. All right. All right, so we're looking at a test a week from today, right? Week out, okay? We still got a little bit of stuff to cover here, so let's get it done here. And I'll get you a review for that maybe tomorrow if I can, or maybe the day after. But yeah, I have a review. I just have to bring it in, and I'll do that, of course. So a lot of you have had me for classes before. If you haven't, I'll get you a review that lists all the topics that you need to know. And it also will have some example problems from previous tests. Okay. All right. So, and it's available in Moodle too, you know, if you want to go find it there. All right. So we good with all that? Any questions? Okay. All right. Because there's another way to calculate this biaxial stuff, and this is kind of an odd sort of thing. I have to warn you. This comes from the days when they didn't have calculators. That's when this method was developed. When they needed an easier way to calculate this stuff. And I really haven't researched this fully, but I suspect a couple of things were lacking. One is they didn't have all these nice calculation devices we have. They didn't have calculators. This is back in the mid to late 1800s. The other thing they didn't have probably was a whole lot of highly educated people to run all these numbers too. So this is another method to calculate biaxial stress. It was developed by an engineer called Mohr, and so it's called Mohr's circle. And Otto was pretty smart, I think. Now the thing to understand about this is it's a graphical calculation tool to find stresses. That's what it is. Okay. So what Mohr figured out is you could represent all the stresses in an element as x and y coordinates and plot them up. And if you do that, they'll plot up as a circle. So he set x equal to the sigma stress on a plane, sigma x1, and y equal to the shear stress. And he was then able to plot up all the stresses into a circle. And then you could look at the points on a circle and figure out what the stress was at whatever angle you were interested in. And so the tools for this are not a calculator, because in the 1800s, of course, they didn't have them. My guess is the best thing they had going was a slide rule, probably. What they used on this was a piece of graph paper, a compass, and a protractor, and a scale. That's how they figured this stuff up. That's the tools they used. All right, now he had to do a good bit of fancy math to make this happen. So here's what he did, and this is kind of his ingenuity here. He started with equation 25, and it's right there. And what he did with it was he just rearranged it slightly. He subtracted this term off from the right side and brought it over to the left. So he got that equation in that form. And then he realized that was kind of similar to the shear equation down below. Okay, so he used equation 25 and he modified it just ever so slightly, as you see there. And then he also put the shear equation 26 under it, and he noticed some similarities. The trig functions changed, but the general form of the right-hand side of those equations are pretty similar. And then what he figured is you could do something a little bit odd to this equation, but it has some very good results if you do that. And what he figured was you could square both equations. Okay? So he squared both equations, which I've done below, and then he added them together, and he got to a much simpler result after some algebraic and trigonometric manipulations with it. Okay, so he took the square of the left-hand side of equation 25 that he modified just a bit to get the sigma x plus sigma y over 2 subtracted there on the left, squared the right-hand side, and that's a binomial, right? So he's got sigma x minus sigma y over 2 quantity squared times cosine squared 2 theta plus 2 times the product of the two terms, so plus 2 sigma x minus sigma y over 2 times cosine 2 theta tau xy sine 2 theta. And then he squared the last term, tau xy squared sine squared 2 theta, okay? And then he squared the shear equation. And on the left, he got tau x1 y1 squared. On the right, he squared the first term, so he got sigma x minus sigma y over 2 squared sine squared 2 theta. Then minus, because we got a negative sign out there, 2 times the product of the outer terms. That's how you do the FOIL method, if you remember that. So it's minus 2 times sigma x minus sigma y over 2 sine 2 theta, tau xy cosine 2 theta, and then the square of the last term is tau xy squared cosine squared 2 theta. And what he noticed then is he could start doing some things and cancel a whole bunch of stuff out, because when he adds these equations together, he's got a plus 2 times that term minus 2 times that term. And even though they come in a little bit different order, of course, that doesn't matter when you're multiplying things together. So what he was able to do was to get that whole middle stuff to cancel out, because you got a plus 2 times all this stuff, and then you got a minus 2 times all that stuff. Now the stuff, again, is in a different order, but it's all multiplied together, so it doesn't make any difference, okay? They're equal terms. One's plus 2, the other's minus 2. Cancel out. And then he also noticed he got tau xy squared sine squared 2 theta plus tau xy squared cosine squared 2 theta. Well, he pulled the tau xy squared out and was left with sine squared plus cosine squared, and that's 1, so that goes away. Same thing on the left, sigma x minus sigma y over 2 squared cosine squared 2 theta plus sine squared 2 theta. Well, that equals 1. So he did some trig identities and canceled that stuff out. And he boils it down and he gets it down to here. Okay? So that's the combination of the shear and normal stress formulas. Now that still doesn't look that manageable, but what he did, he looked at it and said, well, that's the equation of a circle, all right? Because sigma x, sigma y, and tau xy are constants. Those are the things we plug into the biaxial equations that are constants. The things that are the unknowns are sigma x1 and tau x1, y1. So he saw the equation of a circle in there. So what sigma x1 is the equivalent of x. The constant for x is right there, sigma x plus sigma y over 2. And then y is tau x1, y1, and the constant for that is 0. The radius of the circle is then the square root of that term on the right. Okay? So pretty slick, okay? Did a lot of working with that mathematically and got it down to a pretty straightforward form. So what that means is we've had this general form of a circle, x plus cx squared plus y plus cy squared is equal to the radius squared. I mean, that's the basic equation for a circle. This goes to 0. This is sigma x1, and that's tau x1, y1, basically. There's the radius, and there's the constant for x. Okay? So what that's going to be is a circle that's on the x-axis, but might be offset to the right or left of the y-axis. That's what that is, if you remember your analytic geometry. Okay, pretty good. All right. So you can draw up this circle. It's called Mohr's circle, and it has every possible stress in the element on it. Okay, and there are a series of steps that you use to do this. Okay, the first thing you do now, now when it comes to drawing the circle, remember these equations are based on 2 theta. Theta is the actual angle in degrees that you use to measure angles in the element. But what goes into those formulas, 25 and 6, is 2 theta. Okay, so the equation is based on this 2 theta angle that's used throughout the formulas, which is pretty good because if you have a vertical plane, you have one point on the circle, sigma x and tau xy. When you look at the horizontal plane, that gives you a second point on the circle, sigma y and tau yx. They're 90 degrees apart on the actual element, but the circle's based on an angle of 2 theta. So they're 180 degrees apart on the circle that you draw up, and that means they make up a diameter. So if you plot up A, plot up B, find the midpoint is the center of the circle. And then you can construct the rest of the circle by having that. Okay. So what you do with this, and why don't we look at an example here. Follow this, how we would go about this. So let's do this old school on page 390, a graphical approach. Let's find, and we already did this example analytically before. We did it with all the equations. Let's do it with Mohr's circle, and let's do it 1800 style here, okay? So the first thing we got to do is plot up the circle. So the way we do that is we identify what we call points A and B, which are the stress on the vertical reference plane, which is A, the stress on the horizontal plane, which is B, and then the midpoint, which is C. Okay, so we just pull this stuff off. What we have here, if I've had you do this before, sigma x, sigma y, and tau xy. Well, sigma x is negative 52, right? Sigma y is 90, and tau xy is what? Negative 40 there, right? So I can plot up sigma and tau for what I call the A plane, which is the vertical plane, negative 52 and negative 40. Sigma and tau for the horizontal plane, which is we just call point B on the circle, is 90 and 40. Positive 90 there for sigma y, and then the shear is the same magnitude as tau xy, but the opposite sign. And then I can find the midpoint of that line, and that's the C, the center of the circle. So negative 52 plus 90 over 2 is 19. Negative 40 plus 40 over 2 is 0. Okay. So there you go. That's how we start to make the circle. Now, back in the old days here, what we're going to do, by the old days, I mean in the 1800s, we're going to plot up points A, B, and we're going to get the midpoint of it, which is C. C is the center of the circle. You're going to put your needle of your compass in there, and you're going to draw a circle. Put the lead on either A or B, and then draw a circle. Okay? Now, one funny thing about this is the shear has to be positive downward. Okay? I can come back to that later, but that's one little part of this process that's a little funny. The shear is down, which is the y-axis, is plotted down positive. Okay? All right, so I plot the points up on the graph paper, and I've already drawn the circle for you on 390. You could draw on that diameter maybe. Okay, you're going to put the needle of your compass in the center, put the lead on A or B, and just draw a circle. And when you do that, you have all the possible stresses on that element. There they are. So that's pretty good. Huh? Okay. Now again, if you're back in the 1800s, you don't want to be running these formulas with a slide rule or something. It's just too much work, okay? Too much possibility for error too. This is a lot simpler, right? You just plot up A, plot up B, find the midpoint, draw a circle. Okay, now what's the maximum tensile stress in this thing? If you look at the circle, where's it at? If the x-axis is the normal stress. About 100, eh? What's the biggest compressive stress? Yeah, a little bit more than 60, 62 or something, I don't know. Okay? Now, I don't need pinpoint accuracy, you know. When I'm doing structural, I throw a 1.5 safety factor on it usually anyway. And if it's back in the 1800s, you know, I don't got to get, you know what I'm saying? They're just building big stuff out of, you know, mostly steel in those days. They don't need perfect accuracy, right? This is going to be plenty good. What's the biggest shear? Yeah, the shear, I think, is what you were referring to. It's plus or minus 80, right, roughly? Okay? So just by drawing a circle the proper way, you know what the maximum stresses are. You didn't have to touch a calculator or, in those days, a slide rule, okay? So that's a big thing right there. If you're designing something, now you know your design values. 100 for tension, 62 for compression, 80 for shear.
And our average is right there in the center.
Yeah, right. Middle of the circle. Okay. Now there's a little more to it though. I mean, we can do more than just what I'm referring to because, see what else we can do. We can figure out angles too. I can just take a protractor and put it on there. Now, point A represents the vertical plane, right? So if I want to know where that plane is, where the maximum compressive stress lies, what I'm going to do is just put my protractor on A, and then I'm just going to measure the angle to sigma 1, about 30 degrees, roughly, counterclockwise. Counterclockwise, okay? And that will tell me the angle at which that first plane lies, okay? Okay. Now the thing is, I got to remember to take half of it because the circle is based on the 2 theta angles. This is based on, okay, so the actual angle is about 15 degrees, okay? All right. Now where the tensile stress acts will be 90 more than that, and where the maximum shear acts will be 45 degrees more than that, okay? So I just find that angle, I'll just call it alpha. Take half of it, because in reality, the true angle is half of what you get off the equation. 15 degrees, okay? Now the other principal plane will be 90 degrees more than that, because on the circle, you got to go 180 degrees around the circle to get to the other principal plane. So that's 90 in reality. So that'll be 105 degrees to the other principal plane. Okay. So the maximum normal stresses, we got the compressive stress at about 15 degrees and the tensile stress at about 105. Okay. All right. So you can just get this stuff right off the circle. Now the reason they have that shear axis positive down is so the directions match. So if I go counterclockwise on the circle, I also go counterclockwise on the element. That's why they chose to have shear positive down, because if you do that, your directions will work. Okay. Okay. All right, if you want to get the maximum shear plane, you just add 45 to the 15. Because what you're doing on the circle is you're going 90 degrees more to get down to that maximum shear at the bottom of the circle right down there. And in reality, it's half of the circle angle, so it's half of 90 more, it's 45 more. Okay. Well, we got a bit more to do with this, so we'll finish it tomorrow. This was developed on account of not having calculators. However, they started writing up all the theoretical sort of data on this stuff in the early 1900s, and they were using this a lot. So you're going to run into this method a lot, so you have to learn it, even though it is frankly somewhat obsolete because now we can run the formulas pretty easily. But this is very commonly used to describe a lot of things, so that's why we're learning it. Okay. All right, so there's no homework here. We haven't got far enough to do it, but we'll get to some tomorrow. Okay.